Alright, let's start adding some more forces to our encyclopedia that we can use to solve problems. So far we've looked at things like weight. That was equal to mass times acceleration due to gravity. We looked at the normal force, which actually depended on if we were on an incline, if you remember. Let's talk about friction. And so your textbook does a good job of going over some pretty good scenarios about friction. Please read section 6-1. This lecture I'm about to give you, though, is actually pretty much based out of section 5.8 of Survey and Jewett. It's a little bit more condensed and makes for a better lecture. I actually just deleted my lecture from the last book and wasn't happy with it. So what is friction? Well, first and foremost, I think we need to remember that it always opposes motion. What does that mean? Real quick, if we have an object, some mass, and this thing is moving along, we'll say it has some velocity. There's some frictional force, I'll use a italic F to describe it, that is opposing the motion, and that's if it's on something that is not frictionless. So friction, what is it? Well, if you look at two surfaces, maybe this is the surface of a table, and maybe this is the surface of a hockey puck, a book, something that you're trying to slide across. Well, you keep getting smaller and smaller and smaller and keep looking in there, and you realize that things are not smooth at all. It's basically like taking two different saws and grinding the blades up against each other. They describe it as flipping the Alps over upside down and running it through the Grand Canyon. And as we get smaller and smaller, we can just make those contact points more and more. And what we end up with is we actually end up displacing little pieces over to the next location. It breaks off some, and some of this turns into heat, and we lose some energy. And we'll see when we start talking about energy that this makes friction a non-conservative force. But basically, it's just like a grinding of two objects in contact due to usually the weight of an object, or maybe an applied force between the two. And we'll use the normal force to calculate it. So let's talk about a couple scenarios real quick. Let's say we've got this trash can or something sitting on the ground, horizontal surface, and it's got some friction on the bottom of it. Down here at the base, we have some force of friction, and we're going to call this static friction for now. Static friction is the friction that exists when you're not in motion. And it is actually the greatest force of friction that we can have, and you'll see why in just a moment. So if we have some static friction, but we're applying some force, and if we did a free body diagram on this, we would have a friction to the left and a force to the right. So I like drawing the friction on my diagram down at the base where it occurs, but when we do a free body diagram, right now, use a mass center and draw the forces through the mass center. In a little bit, this actually acts some perpendicular distance to the mass center, and that's going to cause what we call a moment or a torque. But for right now, pretend that all of our forces go through the mass center, and that is what we call concurrent forces. So what we have, a force, and this is an applied force, and I'm going to go ahead and make it a little bit smaller than the other one. What's going to happen actually is for static friction, it's opposing motion and it's keeping us from moving at all. If I apply an arrow this long or this much force, it is going to give us exactly the same amount back. The force of static friction is always going to be greater than, or sorry, I'll do that definition in just a second. But that might help clear things up. So for static friction, when we apply a force, the static friction is always going to be greater. And that's deceiving because the force of friction has to be equal in this case for there not to be motion. So it's, even though we can have a static friction, it can be greater, it's only ever equal to the force that we're applying. So let's draw some more arrows. If I applied a force that was this big, the static friction would be the same length. Alright, so these have the same length right there. And this orange arrow represents the maximum friction that could be applied, or the maximum static friction. We can break that number. We can apply a force big enough that is bigger than that value, and if we break that largest value of static friction, we will then get motion. This thing will start to accelerate. So what we see here is that up until the point where the greatest static friction occurs, the forces are going to be equal. The applied force is going to be equal to the static friction will be equal to the applied force until we get to that maximum static friction, that the maximum possible grip that those two objects have on each other, and then it's going to start moving. So a good way to look at this is making a graph. Let's go ahead and just do a x versus y, and let's do the static friction max versus the force, the applied force. What we'll see, let's break this into two regions. One we'll call the static region. That's what we're talking about so far. The static region is, if I apply this much force, it's going to push back that much. If I apply this much force, it's going to push back this much. It is a linear relationship up until we get to that maximum static friction. So this would be our maximum static friction value. As soon as that occurs, we come into the kinetic friction realm, and it drops down a little bit and then levels off. So this is what we will call the kinetic friction. And just based on the word, static means no motion, and kinetic literally refers to things that have motion. We see that as soon as we break this maximum up here, that the kinetic friction, which we'll call F sub k, if this is F sub s, the kinetic friction is always a little bit less. And so when we see values given to us, in a problem, the static friction will be a larger value and cause a greater force of friction than the kinetic value. You should have done something like this in lab, where you held something up at an angle, maybe like a wooden plank, make some angle theta, and you raise this angle until the mass started sliding down. It started accelerating. And once it starts accelerating, that was what maybe you called the critical angle. And I'm going to go over this I'm going to derive this in a second. I just want to reinforce this static and kinetic thing. Once the component, remember we take the mass times gravity, pointing straight down, then we can break this into parallel and perpendicular components. Once this component that's going down the incline, mg sine theta, once mg sine theta is bigger than the frictional force, it's going to accelerate. And then what you maybe had to do was bring back the angle a little bit lower so that it required you to maybe nudge it with your finger or something. You gave it a little tiny bump, and then it didn't have an acceleration, it moved down with a constant velocity. Alright, I'm going to do this whole problem again in just a second. I just wanted to show the difference. The static friction was bigger and it required a larger angle to get motion to occur, and then after that it actually accelerated and sped up. It didn't move with a constant velocity. To get it to move with a constant velocity, we had to make the force of kinetic friction equal to that mg sine theta. Alright, how do we calculate a force due to friction? We have static and kinetic friction. Well, the force of static friction is less than or equal to mu static times the normal force. This is referred to as mu. And the less than or equal comes to that point that if I'm trying to move something and it has static friction, it has a maximum friction maybe of whatever this orange arrow is. So this is its static max. If I apply a force that's this big, it's only going to give me a static friction back of that big until we get to that breaking point and when they're equal. And we use that breaking point as to know when motion occurs. When they finally equal each other, or when the component going down the incline is bigger than that static friction force, then that's when it accelerates. So use that to solve problems. And then we can define the force of kinetic friction very similarly as equal to mu k times the normal force. And I'm going to derive mu for you in just a second, but mu is typically a number, it's a unitless value, and it's between 0 and 1. We can have values larger than that. For drag racers to do what they do in their drag cars, go super fast, they accelerate ridiculous speeds. I want to say they put out coefficients of friction up to like 7 or 8. It's like 7.0, not in 0.7, but 7.0. And they're doing that by this wing in the back. They're getting pressure as they build speed, which increases the normal force, but also they are doing burnouts, causing heat on the tire. There's lots of things that can increase that value. But this is how we calculate it. Always remember that friction is always opposing motion. It's always in the exact opposite direction. If I have a mass moving this way, that friction is going to be working this way, and this could be in some XY plane. Hockey puck sitting on a surface, sliding up and to the right, well, friction is going to work down and to the left. So this could be its velocity. Okay, let's do one last thing. Let's figure out how to calculate mu s and mu k. We could do this experimentally. So let's do an inclined plane. Alright, let's put a mass on here. First thing I always do is draw mg straight down. And on this inclined plane, let's say it's that wood plank and an eraser or a book or something. And we change this angle theta until it begins to slide. Well, if that's the case, then we're going to be dealing with some sort of friction going in the opposite direction. And let's start with static friction. When we draw the weight down, we need to break it up into its components when it's on an inclined plane. And that gives us an mg sine theta in the direction parallel to the plane, and an mg cosine theta perpendicular to the plane. And we got to draw one more, the normal force. Alright. We now need to apply Newton's second laws. If we sum the forces in the perpendicular direction, that'll be equal to the mass times the acceleration in the perpendicular direction. Now this thing, it's not going to come off the surface in this scenario, so we can say there's no acceleration in that direction. So what are our forces? We have a normal force going up. We have this component going down of its weight of mg cosine theta, and that's all equal to 0. So we just found its normal force. Y'all should remember how to do that. Call that equation number 1. And let's sum the forces in the y direction. That's going to be equal, or not the y, the perpendicular. That's be equal to the mass times the acceleration in the perpendicular direction. If we are talking about a static case, that means there's no acceleration. Alright, so we can also say, oops, sorry, these are parallel, not perpendicular. We can also say that in this direction, down the incline, that the acceleration is 0. So what do we have for our forces? Well, we could call I want to call that positive. Then we'd have an mg sine theta and a minus force of friction. And that all equals 0. So we see the static friction would be mg sine theta. So if you knew something's mass and the acceleration, we could find the angle to give us and the object, we could find the angle that'll cause the object not to move because it's under the influence of static friction. And what we could do is realize take this equation right here, equation number 1, and we can substitute it for mg. If I solve that for mg, I get the normal force over the cosine of theta, and that would equal mg. And then I can plug this in right here. And that's going to give me the static friction being equal to the normal force over the cosine of theta times the sine of theta. And the sine of theta over the cosine of theta is equal to the tangent of theta. So we just get the normal force times the tangent of theta. Alright, what is this equal to? Well, we said the static friction is equal to mu times the normal force. Well, if that is equal to the normal force times the tangent of theta, cancel, cancel, we get mu static equal to the tangent of theta. So you can literally take this mass, raise this angle until it starts moving, and once you have that angle, you can take a ruler and measure the rise over the run, right? So we could measure the rise over the run for a perpendicular, and that would give us, that is equal to the tangent, right? Opposite over adjacent. That's equal to mu. So I think you did that in the lab. The only difference for kinetic friction is that you have to give it a little bit of bump first, and I had a note written, just a second, hold on. Basically that once you give it that nudge, you've given it some force bigger than, so it has a net force big enough to exceed the static friction. Then kinetic friction takes over, and it's independent of speed or velocity. So even if the thing starts speeding up, we just have a kinetic friction taking over. If the component of the weight is equal to the kinetic friction, so we have this component right here. If mu k times the normal force is equal to that mg sine theta, and this normal force off our free body diagram was mg sine theta, or m cosine theta, and that equals mg sine theta. We just derived mu kinetic again. So this would be, you'd want it to move down with a constant velocity for this one. Over cosine theta or tangent theta. Alright, that's literally how it's derived. Obviously, it doesn't have to be on an incline, so just know that it always opposes motion if we apply a force. I'll do an example in the next video where I apply a force down at an angle. It already has some mg going down. This is now going to have an extra little bit of a normal force going up, because there's some component of this force also pushing down in the y direction. So that's going to increase the frictional force. If I added a mass on top of the other mass and they're linked together somehow, then that frictional force goes up too, right? Because the frictional force is equal to mu times the normal force, and the normal force is equal to, in this case on a flat surface, mass times gravity. So if the mass gets larger, the frictional force goes up. If it's on a rougher surface, mu will cause the frictional force to go up. And if we're on an incline, we'll get a fraction of gravity, right? Not, our normal force gets smaller as we go from a a zero angle to a large angle until there's no normal force at 90 degrees. Alrighty.